Hello, everyone. All right, topic number 5. Again, guys, we're dealing with, right now, this is Physics 120. We're dealing with the Serway and Vuille book, Volume 1, 11th edition. Volume 1, 11th edition of the Serway and Vuille book. Sometimes it's called the Serway book. So it's the 11th edition. So we've got these 8 problems that I think are pretty useful to you that I'd like to kind of look at. We're talking about energy in topic 5, the equivalent to chapter 5, as we said, the 11th edition of the Serway book. Great book, you guys. The whole series, volumes 1 and 2, are just excellent. Mechanics and electricity and magnetism, so we're fortunate to have that. Let's talk about energy and work and things of that nature. It's a hard concept to talk about in some regard. Energy is definitely a little tougher to talk about than work. Energy and work are closely related to one another. Let me try to build a little bit of a hierarchy here, if you don't mind. The word energy itself is from Greek words. En is in, from an ergi, from ergos. En, ergos. Inside of it is work. En is in, ergos is work. In it is work. In it is the capability to do work. There's not really a good definition for it. We do say though that energy has the ability to do work. Now, what's work? Well, like everything else we do in physics and so many other things, and in mathematics for that matter, you got to have a measuring stick for what's going on. Let's put it this way. If I were to try to pick up, I don't know, let's say a 100-pound weight, and I'm going to try to climb, let's use the let's use the MKS system of units. Let's say I picked up a 500 Newton weight, somewhere in the ballpark of like 110 pounds or something like that, let's say. A 500 Newton weight, I picked it up and I tried to climb the stairs with it somehow. I tried to climb 10-meter height, used the stairs, and I went up a height of 10 meters fighting against gravity. That's not easy. You know what's even more difficult? Try doing it for 20 meters rather than 10 meters. Well, if I went twice the height, I did twice as much work. If I went 10 times the height, what's 10 times 10 meters? It's 100 meters. If I climbed 10 times higher than 10 meters, I need 10 times the work to do it. You don't get something for nothing. If I'm going to climb 10 times higher, it's going to be 10 times more work for me to do something like that. Maybe that's believable. I think it is. In other words, I'm having to overcome a force, the force of gravity, and I'm exerting a force over a distance d. That's equal to the work I did. I tried to cover, a big distance. And I tried to cover 10 meters going straight up. I fought, and I did what I did. So if I had a 500 Newton mass, a mass that had associated with it due to the gravitational field of the Earth, because mass and weight are not the same. If I had a weight of 500 newtons, that's a mass that has a weight associated with it because of the gravitational pull of the Earth. A 500 Newton object in terms of weight, and I'm moving at 10 meters. 500 times 10 is 5,000 newtons times meters. 1 Newton times meter, 1 joule, is called 1 Newton times 1 meter. If you exert a force of 1 Newton over a distance of 1 meter, you did 1 joule of work. So right here, newtons times meters, we'll get into this in a little more detail some other time. This is 5,000 joules. You did 5,000 joules of work, or the machine did that much work, whatever. Let's say you could do it. Pick up a 500 Newton object and you move it through a perpendicular distance of 10 meters. 10 times 500 is 5,000, that's 5,000 joules. What if you were picking up, let's say you were, let's say this is some science fiction movie and it's King Kong picking up a 5,000 Newton weight and he's going 10 meters. It's a little different story. 5,000 newtons times meters, 50,000 newtons times meters, that's 50,000 joules. This is 5,000 joules. This is 10 times more work. It makes, I am trying to knock myself out today. I really am, I swear to God I am. Okay, this is, all right. So here we go. Let me figure this out. Okay. So once this is 5,000, this is 50,000 joules, this is 50,000 joules, that's 5,000 joules. This is 10 times more work being done than was done in this instance. Makes sense to me. You move the exact same distance, but you were carrying an object that had weight 10 times more. What if you kept the same object, not as heavy as the 5,000, yeah, but let's say you went up the stairs, not 10 meters in vertical height, not 10 meters in vertical height, 100 meters in vertical height. This is also 50,000 joules. This is also 50,000 joules. What are you talking about? Well, you don't get something for nothing. Yeah, this is a lot easier for you to carry. It's 10 times lighter. Yeah, but I got news for you. King Kong might find it easier to carry. It's 10 times lighter, but he's going to have to go 10 times further. So in the end, the multiplication yields the same answer. So this is a very important thing related to work, you guys. How this whole thing plays out. This is a big thing related to work, and this is some of the stuff we can look at. Well, let me say a couple things. I mean, there's kind of just look a little bit ahead of the book. I don't want to, to me, there's no, this is fine. I'm going to do what I was initially planning to do. This is okay. So we're looking at this. So we'll look at it. Let's get more into this. This can get a little on the messy side. We're not careful about it. Okay. Yes, this board does not want to stay still, and I will certainly sustain a serious injury before I leave today. I just can kind of feel it. I mean, it's just been that kind of. This is not working the way. All right, so we're going to not worry about it. This thing only goes down to here, so I think we're okay. So that shouldn't be too bad. All right. Okay, we got to talk. So you're looking at this, guys. There's a lot that goes on. A lot I'd like to tell you guys. I guess we can cross every bridge we need to cover it. They got this thing that you don't really absolutely need to know for this class, but it's something interesting to kind of look at. This is a good way to look at it. A better way to look at it is f times d times the cosine of theta between the two vectors. If you're doing a force F, looking like that, and you're displacing it over a displacement d, and we can call that a vector too, and we can call this theta. You always gotta make the F vector and the D vector, you gotta make them line up. And the way you make them line up is you drop a horizontal projection either from the D to the F, or in this case what I'm doing, from the F to the D. You drop a horizontal projection down and you do it. And that's kind of, you can't just multiply these two quantities. You can't just multiply these two quantities. You've got to get the cosine of theta between them, line them up in one line. Either the line goes this way or the line goes that way. But you got to line them up in one line segment, and that's where this comes in. This is a simplified version of this, but this only works when theta is 0 degrees, when they're right on top of each other. That's when this works. This is really the technical way to look at it. In a more technical way, I don't want to get too far into this, I don't want people to lose a whole lot of sleep on this thing, but in general, when you got two vectors, a vector A and a vector B, they call this thing the dot product. These are two vectors, and you get a scalar quantity. Vectors have a magnitude and direction. Scalars just have a magnitude. So, vectors have a magnitude and a direction associated with them, as you can see here. Whereas the scalar just has a magnitude associated with it. If you do a dot product of two vectors, you get the size of A, the size of A vector times the size of B vector times the cosine of theta between them. In three-dimensional space, and we're not gonna lose a lot of sleep on this. I just wanna, there's an X component, and this I hat means let's go in the X direction. Then there's another one that goes in the Y direction. We put a J. IJK is what they do. And this is in the Z direction, they do this. For B vector, it's BX I hat, BY J hat, BZ K hat. If you do the dot product of these two things, there's a lot that goes on here. I'm almost regretting telling you this. Don't lose sleep on this. You don't need to know this for this class. But what happens is, believe it or not, AB cosine theta is the same as AX dx plus AY by plus AZ bz. Dot product is this, the dot product A vector dot B vector equals AB cosine theta, scalar number, same entity, A vector dot B vector. The dot product of two vectors is this scalar. This scalar right here and this scalar right here, they are equal to one another. There is some beautiful math. It almost looks like, what? It's like you're making this up or something like that. It almost looks too convenient in some regard. There is some really beautiful mathematics that goes into proving why this is true. That mathematics is not for our class right now, but I know we can do it. We were patient with it. If you got a calculus background, we can certainly get it done. A lot of people do have a calculus background, regardless of the classes that they're taking. Even if it's a non-calc class that they're taking, a lot of people have calculus. And every class is challenging and fun, regardless of the background that we have in it. I know a lot of people have a calculus background, and we can do this. We can do this. It's not really difficult. It's not really difficult for us to do it, but it's very tedious. It would take a long time. And like I said, I know a lot of people have the background to do the calculus. Maybe in other circumstances we could talk about something like this. But anyway, I just needed to tell you that. This is where this is coming from. And of course, it's challenging when the board moves, so you got to keep your eye on what's going on. It's like we're fishing or something, trying to reel something in. So we've got all this. So we're looking good. We're looking good. All of this gives you this. Okay? Something good to look at. Okay. See what else I can say. We said that there's another thing here. It's a can of worms I don't think we want to open. I'll probably go there another time. They got this thing called the cross product. Let's say it's the same vectors. A vector looking like this, B vector looking like that, and that's not an X, that's a cross product. A vector cross B vector is the same as evaluating a determinant forgive me. Let's see. All right, guys. It's called evaluating the determinant. With this situation here, it ends up throwing something at you. I might have just fixed this thing on accident. Okay, I'm sure I did not, but it's just, I think I might have. Okay. Yeah, maybe I did. Okay, hold on. Okay. All right, this is going to be, I'm sort of regretting showing you that. I'm going to show it to you real quick, just so we have it in our mind, I guess, at some level. You're evaluating determinant here, my minders. This is column 1, row 1. So let's see what we got here. Column 1, row 1, add row 1, add 1 and 1, get 2, it's even. It's going to be a positive answer, so it's going to be AY, BZ. I'm trying to give you some room here, guys. AY, BZ minus AZ. Forgive me. Let's look at it carefully here. You're crossing out here. Row 1, column 1, 1 and 1 is 2. 2 is even, so it's AY, BZ, BY, AZ. You're doing a similar argument here. Let me just kind of get this out of our life here, guys. It's going to be, in this case, for the J vector, it's going to be a negative J hat. Because it's row 1, column 2, 1 plus 2 is 3, it's odd. AXBZ and BXAZ. So, or AZ, let me just see here, right. AZ BX. Then we come down here, we got K hat. This is row 1, column 3. Row 1, column 3. 1 and 3 is 4. AXBY. I'll explain in a second what the heck's going on here, guys. AXBY, AYBX. There's a number of ways this can be written. They all mean the same thing. Okay. Now what? Well, what happened was this is called the cross product. That's different than this. This is the dot product. This is the cross product. The dot product takes 2 vectors, force and displacement, and gives you a scalar. The scalar in this case is work. Work is a scalar quantity. It's not a vector. It's independent of path, the work that's been done. So work is a scalar quantity. You arrive at work by doing a dot product of 2 vectors. You're basically doing, for work, it's coming out as F vector dot D vector. A dot product of 2 vectors gives you a scalar, and that's work. And we said the work, F vector dot D vector is FD times the cosine of theta. We also said that in this case, if this was F vector dot D vector, it'd be Fx dx plus Fy dy plus Fz dz. Just plug in the actual formulation. As I said, I am confident that we can do this. We can prove that. If you guys got a calculus background, a lot of people do. A lot of people have a calculus background, a lot of people don't have a calculus background. I think anybody can get a calculus background if you take the time to do it. If you don't have a calculus background now, when you do have it, we can easily go through it. For those of you who do have the calculus background, we can prove this. It's very tedious, not very difficult, but it's quite tedious to do. We can get this. Same thing here. We can prove this, A vector cross B vector, and get all this answer. Again, not really difficult, but very tedious. What's going on here? This is really useful when you're talking about work. Later on, when you talk about torque, this is really useful. We're not going to need to know this kind of specificity, you guys. We're not going to need to know this kind of specificity. Okay? We don't need to know that. But we do know one's a vector, one's a scalar. Now, this right, the crazy thing is A vector dot B vector. And like I said, those of you, like if you're in, how I was give this to my calc-based class, they kind of expect this to be known in the calc-based class, but sometimes they won't even go this far either, or at least with this kind of specificity for us to actually get it. So it's an interesting point in its own right. If you look at this, as we said, you're looking at, based on everything I just said, we're saying this. We also said this. You saw me. Magnitude of A, how big is A? How big is B times the cosine of theta? By the way, how big is A? A is a ripoff of the Pythagorean theorem, is what it is. AX squared plus AY squared plus AZ squared, add them together, get the square root, you get A. B, the magnitude of it, the magnitude of the vector, a lot of times they write it like this. A is the magnitude, the actual size, the length of the vector. B is the length of this vector. So that's what we're trying to say here. This is, again, we're not going to lose a tremendous amount of sleep on this, guys. But at the same time, I don't want to cheat you either. At the same time, I don't want to cheat you either. I want to say what I say. So we've got something looking like this. That's interesting. The other one's a vector. A vector cross B vector. And we'll see this when we get to torque. I'm not going to give the application anywhere near as strictly as what this is right here. Anywhere near as strictly, if we look right here, guys, anywhere near as strictly as what I said right here, I'm not going to give you that application. We're not going to apply it like that, but it's good to know. Some beautiful mathematics goes into this, when they do this. We got I hat, we got AYBX, AZBY. AY, BX, let's see here, what we did here. For you guys, this should have been AYBZ. AYBZ, forgive me on that one, guys. The other one, X and Z, the other one, X and Y, looking good, okay. So, AYBZ, the other one is plus a negative, okay, plus a negative, AXBZ AZBX K hat AXBY YBX. Okay, this stuff's, it's crazy just to write it down sometimes. Anyway, the proof of this stuff, guys, the proof of all of this stuff is really something else. Is really something else. There is some beautiful mathematics that goes into it. So, I mean, I think it's really some real beautiful mathematics that goes into this stuff, you guys, to get you to where you need to go. So this right here, YBZ AZBY, there it is. Okay, now, here's the weird thing. If you wanted to find the magnitude of this cross product, it's as simple as this. It's A times B times the sine of theta. It's A times B times the sine of theta. Are you telling me this entire big song and dance, right up here at the very top of the board, this entire big song and dance right here, if you found its magnitude, it would be as big as the size of A vector. It would be as big as the size of A vector times the size of B vector times the sine of the angle that's between them. Yeah, I'm exactly saying that. I'm exactly saying that. The cross product takes two vectors. You got A vector and you got B vector, let's say. This is theta. The size of A times the size of B times the sine of the size of A times the size of B times the size of theta will give you the magnitude of the cross product. This is the cross product. Square this, square that, add them together, get the square root. Its size will be as big as this. The proof, the mathematics, is pretty fascinating stuff. Not really difficult, but very tedious. A vector cross B vector follows the right-hand rule. You take your right hand, you start at where you do the cross product. You're doing A cross B, right? If you're going to do A vector cross B vector, you roll your fingers from the A vector to the B vector, and your thumb points in the direction of A vector cross B vector. So, I think there's a, let's say it'd be, comes right out here. Comes right out at you guys. Perpendicular to it. If you go B vector cross A vector, you'd have to take your right hand this way, go B vector cross A vector, roll your fingers from B vector to A vector, your thumb goes in that way. It goes into the other room. This thing points into the other room. The size doesn't change, but the orientation changes. Why do they do that? I don't want to get into why they do it. They found out this stuff seems to happen in physics, and they developed mathematics to talk about it. To me, it's pretty fascinating that this complicated entity right here, AYBZ minus AZBY, and this complicated entity, AXBZ minus AZBX, and this complicated entity, AXBY minus AYBX. If I take this quantity, figure it out, square it, take this quantity, figure it out, square it, take this quantity, figure it out, square it, add the squares together, get the square root, the size of it's going to be the size of A times the size of B times the sine of theta. The size of A is equal to this, the size of B is equal to this. In both cases, this is for both. This is for both the cross product and the dot product. I'll try to get into more detail on this. This stuff's better done in person. This stuff is better done in person when we're doing this stuff, obviously. But I like that. Greeks have a saying, if you enter the dance, you gotta dance. And you know, you guys know me by now, I love to repeat myself, and it does help sometimes. I know my wife wants to kill me because I do it all the time, but I do love to repeat myself. And I think it's going to help you guys when I do repeat myself on this stuff. You saw me talk here, I kind of beat it into the ground. Is there a takeaway on this whole thing? Well, there's a couple takeaways. The dot product is a scalar, and that's how we find out work, and that's pretty important. And that's what we did. That's what we did here. This is a more general case of what's going on. This is how you do. This results. This dot product means this. On the other side of that, okay, that's a scalar. That's a scalar quantity, not a vector. The cross product, when we get into angular momentum, when we get into torque, they use cross products. Angular momentum and torque are vectors, whereas work is a scalar. The two vectors multiplied together as a dot product gives you a scalar quantity. Two vectors dot product together give you a scalar quantity. Two vectors cross product, do the cross product with two vectors, you get another vector as an answer. The size of the vector is equal to this. Keep it in the back of your mind. A lot of you guys have already seen this somewhere in some math class that you had. Many people have not seen this. Either way, we're not going to lose a lot of sleep on it, but I figured I owe it to you a little bit to talk about it. I cannot emphasize how beautiful the mathematics is that takes this and proves that it's also equal to that. And other mathematics that you would do to take the cross product of two vectors and get this quantity. And then know that that quantity is this size, and it points out perpendicular from the plane formed by those two vectors according to the right-hand rule. The cross product is a vector. Cross product of two vectors results in a vector. Dot product of two vectors results in a scalar, and that's what we did right here. Dot product of two vectors, that's a scalar, that's the work. The mathematics is, I can tell you, very powerful, very beautiful, not incredibly difficult, but all of it's quite tedious. Not our problem right now. Something to look at in the future, though. If you want to give yourself an interesting challenge, definitely something to look at, you guys. All right. Actually, I like this rule. I think it makes me feel important. Pointing all over the place. I'm doing some presentation. Okay, so we're looking okay, guys. Let me erase this a little bit, and then erase some other stuff, and we'll start knocking this stuff out. And I think we're going to be okay. We're going to be all right. It's a little more than I wanted to say, but I'd rather say a little more than too little. And then you guys can kind of read that out a little bit if you want. I mean, just something to maybe get your interest. Next time you're in a math class like that, maybe challenge the teacher or the teaching assistant and say, hey, well, by the way, can we take this a little further? Can we talk about it? Is there a good place to look at a proof? It is remarkable, some of the proofs that are out there. Some are easier to look at than others, and some to me, I don't think are that helpful. They're not intuitive enough. That might just be me. That might be my shortcoming in the whole process. All right. So we've said a good amount. Let me kind of do something here. Get rid of a little bit of this. And again, these 8 problems are what we're going to try to knock out. Talked about work. There's another thing. I don't want to get into all the different ways you can look at this. What I would love to do is throw this whiteboard out the window if anybody doesn't mind. Maybe that would be something to film as well. The only problem is I don't know if the window's big enough, so it's okay. Let's try this one more time. All right. Okay, let's start. There is a universal law in physics. There's a couple of them. I might as well tell you a couple of them now. Momentum is always conserved at all levels. Angular momentum is always conserved. And getting back, we'll talk. I don't have to know that now. This you do need to know now. Energy is always conserved. The energy initially present in a closed system is equal to the energy that's finally present in the closed system, or at least the work that's been done. Somehow something happened, even with friction. If I'm pushing something against, if I'm pushing something against the floor is generating the floor and the crate, and I'm pushing across the floor. There's friction, and it heats up. That heat energy is energy. Some way or another, I have to be able to account for the energy. They go into this in different ways in different books. Energy initial. Stuff's easier done than said. Maybe we can just, within the context of the problems themselves, make more sense out of it. Energy in the universe is conserved. Energy is not created or destroyed in the universe. Energy is not created or destroyed in the universe. Energy is conserved in the universe. If we're talking about a system, a mechanical system, they talk about a lot of things you can say here. Where you want to go with some of this stuff, how I want to discuss this. There's this thing called potential energy. Potential energy is energy that's stored. Give me some examples of potential energy. Well, how about a spring? I've got this dart gun that I want to, I'm shooting it against the wall and stuff like that, and I compress the spring. The more I compress the spring, the more energy that's in there. Once I release the spring, what happens? That potential energy becomes kinetic energy. Kinetic energy is the energy associated with motion. So potential energy is often associated with position. PE, potential energy, KE, kinetic energy. Didn't we talk about King Kong climbing the stairs and what was going on? Well, it did work. It was F times D times the cosine of theta. If he's going straight up, it's just this. What was he doing? Well, I think what he did was, he's going to climb the stairs for a reason. He climbed it, and then, let's say he took this whiteboard. You see, I'm in love with this whiteboard, right? He takes the whiteboard, and then he decides to, there's an abandoned lot right outside the window, nobody's there, and he just throws it out. What happened? What happened was, the object had potential energy because it's elevated. Once he throws it out the window, as the object falls, it loses potential energy, but it gains kinetic energy. At the very bottom, it's going very fast because all of the potential energy has been converted to kinetic energy. Kinetic energy, kinesis, kinao, kinesis. Kinesis means I move, or kinao, I move. Kinetic energy is energy of motion, energy that pertains to motion. Potential energy is energy that's oftentimes stored. Where? Maybe it's stored in a molecule. Maybe it's stored in the spring. Maybe it's stored in the position that the object that King Kong carried up the stairs did before he threw it out the window. What do you mean? Well, he climbed a height h. He climbed a height h, and how did he do it? Mass times g, m times g is the weight. He took the weight mg and he put it through a distance h. Wait a minute. F times d. F times d, he's doing a force mg, he's doing it over a height h. That's the potential energy of position. He carried that. Kinetic energy, I'm not going to derive it yet, maybe I can do it later. 1/2 mv squared. Guys, I'll cut to the chase. Potential energy initial plus kinetic energy initial of the closed system in the right circumstances. Again, I don't want to blind you with all the trees here, guys, in the forest. I'm not going to talk about the forest nor the trees. Let me just give you potential energy plus kinetic energy equals potential energy plus kinetic energy. Initial potential energy plus initial kinetic energy equals the sum of the initial potential and kinetic energy equals the sum of the final potential and kinetic energy. So this is going to help us do a lot of stuff. So there's some pretty neat stuff that happens here. Let's see what I can say here. We did say, the work that gets done tells you the energy that you expended. You understand, when King Kong climbed 100 meters straight up, effectively straight up, with a 500 Newton object, or exerting 500 Newtons on the object, and the object happened to weigh 500 Newtons, 500 Newtons times 100 meters was the 50,000 joules that we were talking about. If he decided to climb with something that was 10 times heavier, it'd be 10 times. It wouldn't be 50,000, it'd be 500,000 joules. If he decided to climb, in a whole lot of ways, what you're doing is you're doing the weight that he's picking up times the distance traveled. The weight, you guys, is mg times h. Mg is the weight, and mg is the weight, and h is the height that he travels. It's as simple as that. Remember, there's like I said, the shortcut here is F times D. I'm not going to put cosine theta there right now. Technically, it's got to be there. But let's say everybody's in line, and you got this. If you're talking about potential energy, how much stored energy you understand? This is what makes heights dangerous, you guys. If I'm a construction worker and I climb to a great height, I better be strapped into something. Why? Because I've got a lot of potential energy in relation to the earth. What does that mean? I mean, I'm in a dangerous place. There's a lot of, if I fall at the very bottom, I'm going to be going very fast. Okay? So, the potential energy here regarding position is mg, that force is mg times the distance h. That's not right there. Where do they get kinetic energy, though, I'm wondering? I mean, they make the claim kinetic energy. Kinetic energy, or changing, or delta kinetic energy. Delta kinetic energy is 1/2 mvf squared minus 1/2 m vi squared. Yeah, well, if you started at zero, if you started at zero speed, then it's just this, 1/2 mv squared. That's where we're getting that from. So that's very interesting. Let's ask a couple questions. Maybe I can derive it. Work is F times D. Do you agree that F is M times A? We talked about that. Force equals mass times acceleration. That's D right here. I got some more questions to ask. Is the distance traveled, if you are giving something an acceleration, you guys, is the distance traveled Vf squared minus Vi squared over 2a? I'm wondering, what are you doing? You'll see. You'll see. Distance traveled is this. Take a close look at that. If you think you see something, you probably do. A and A cancel. Two's right here. The work that's done, the two's on the bottom. If you started from speed 0, mvf squared, that's where you're getting it. I realized 10 minutes ago I said I wouldn't do that, but I just did. Okay, so there it is. Okay, it's not that bad. It's not bad. It's not bad. We're talking about the KE also, as we said. I want to kind of just watch out here and see what we can say. It's looking pretty good, guys. There's a lot there. So let's go. I mean, I think we got what we need. We have what we need from what we did in the past. If the past work is a little bit of an issue, go back and look at it again. Read the book, look at my notes, look at my solutions to the problems, look at the video. The video should be okay. If not, the notes should be fine too, guys. I'm a little more old school. I like to look at good notes. Hopefully the notes are good for you guys. Okay, so sorry guys, we're trying to make this look good. We got this, okay. All right. Let's talk. I think we're there. I think we can do it. Try to find a little bit of chalk here that I kind of can. Christine, I may ask you for more chalk, but I think I'm okay now. I think I'm okay. There's a lot here. It's small, and I don't know if I'm gonna. But I think we're gonna be okay. We're good. We're okay for now. But I'll ask my colleague for some help when I need it regarding this thing as well. Okay, it's looking pretty good. I think we're okay, guys. I think we're okay. So you see what I got here? I think we just start doing the problems. Okay, let's see what we got. So I'll leave that up there, and then I'm going to go to 5 onwards, you guys. Let's see what we got. My colleague bring me some chalk, I think. So I think we're. Thank you, Christine. I appreciate it. I'm probably overreacting. Oh, okay. Well, I hope I'm overreacting. I think we're fine. We'll be fine. We'll get more. We'll find it. I think we're fine. I think I'm kind of overreacting about it, but I think we'll be all right. I think I got enough here. For some reason, it's just not. I think we'll be fine. All right, guys. Let's look at 5. Problem number 5. Starting from rest, a 5 kilogram block slides 2.5 meters down a rough 30-degree incline. The coefficient of kinetic friction between the block and the incline, use of K, is 0.436. Determine A, the work done by the force of gravity. B, the work done by the friction between the block and the incline. C, the work done by the normal force. Qualitatively, how will the answers change if a shorter ramp and a steeper angle were used to span the same vertical height? This is an interesting question all the way around. Let me talk to you about it. I got a feeling a lot of times you're gonna, this is all in my notes, guys. This is all on Canvas. So if this ain't working great for you, just go to my notes, okay? They're saying essentially, what's going on here? We don't care about the path that's been taken. Now there's a lot going on here. I've got it here, I've got it here. This is 30 degrees. This is
is this. I mean, I don't know, we've kind of beat this one into the ground pretty good, guys. We got it like this, you know, you saw me do something like this. If this is theta, if theta equals 30 degrees, this guy equals 30 degrees too. You got this, you got this, you got this, you got mg here, you got mg sine theta here, you got mg cosine theta here. This is theta, this is theta, etc., etc. We need to figure out what's going on here. There's friction that's fighting this guy. It's always fighting the motion. There's a lot you can say, I guess. Cosine of theta, theta is 30 degrees. Remember, the normal goes this way, straight up. This dot product, you know, the dot product of two things that are at a 90-degree angle is 0. This is an interesting point, guys. If I was strong enough to pick up a 500-pound weight and walk in a horizontal direction, even if I walked 1,000 meters, technically I did no work. I know that sounds ridiculous from a lot of standpoints, including the standpoint of common sense. From the standpoint of physics, the weight, I am lifting the weight straight up, and I'm going this way. There's a 90-degree angle. What's the cosine of 90 degrees? 0. You can only do work in the sense that they're using in the definition here if the angle under consideration is something less than 90 degrees. It can't be 90 degrees when you're doing it. There's got to be some component, there's got to be some way that there's a substantial non-zero component falling onto the other vector. The vectors are straight up and down. Now, how many people believe that if you're picking up 500 pounds and walking 1,000 meters, that's not work? There's other work going on. Your muscles are doing stuff, calories are being burned, there's things going on with your body. From a mechanical standpoint, they say that's not work. Okay. They're saying this stuff, they're saying how far it goes, how far it's going to slide. Friction opposing this means cosine of 180 degrees is -1. It's going to be a negative. There'll be negative work done in this particular regard when we're doing this. So let's see what we got. Starting from rest, a 5-kilogram block slides 2.5 meters down a rough 30-degree incline. The coefficient of kinetic friction to the block, mu sub k, so there's a lot going on here, so I don't know where you want me to go, guys. 5-kilogram block, it's sliding down 2.5 meters. Mu sub k, because it's moving, is 0.436. So we're looking good. We got all this stuff, guys. The work done by the force of gravity. What's gravity doing? This guy is sliding down a distance d. I need to know the fall down, which is this. I don't care about this. I care that it went from here to here, which is a fall down straight down like that. This is also a 30-degree angle. The height of the fall down is d sine theta. The height of the fall down is d sine 30 degrees. The work that gravity did, it took the mass and it brought it down. It brought it down. Plug in the numbers. M is 5, G is this. D is this. The sine of theta, 0.5. Grind out all the numbers, guys. That's A. B, the work done by the friction force between block and incline. Well, I'll tell you what. Let's find out how strong the friction force is, and let's move it over distance D. Friction will dissipate. It'll do negative work. The friction ain't going to move it. The friction's going to try to stop it from moving. If we can figure that out, then we're set. That's the same as use of K, mg cosine theta, that's the normal. Mg cosine theta is the normal, times use of K, that's F. That's the friction force, times D. And that's the work done by friction. Plug in the numbers. 0.436, 5 kilograms, 9.8, cosine of 30 degrees, times 2.5. Grab the numbers up there. Frictional force is this. Forgive me, it's got to be negative. Got to be negative. Because it's fighting it. You know, it's opposing. It's opposing what's taking place. That's B. C, the work done by the normal force. Interesting. Let's talk. This is the normal force, ladies and gentlemen. This is the normal force. This is the displacement vector D. This is the displacement vector D. They are at a 90-degree angle with one another. Can we say work was F dot D? In our case, let's see what the friction does, or the other way, it doesn't matter what it does. Both forces are perpendicular to it. The frictional force dot D. That's F D cosine 90 degrees. Why is it 90 degrees? I want to know. I just delivered that speech. If I was strong enough to pick up 500 pounds and walk 1,000 meters, I've done no mechanical work. My body having to do all the chemical reactions for me to do what I just did, yeah, that's another story. The energy's there. It's accounted for. It's accounted for. What had to take place there. How it's accounted for, that's another story. We're better placed talking to some of the biologists at this great school about something like that, how that all plays out, right? How the biology all that works. So there's energy going on. There's energy being dissipated. There's the food you've eaten is being converted to energy for you to be able to do that, even though technically you're not doing mechanical work. Because they're at a 90-degree angle with one another. Okay, so what do we got? So we said this. This is B right here. C right here. Let me also do it here. Zero joules. When this and this are perpendicular to each other, it's like me carrying the big weight. It's going to be zero. It's going to be zero. D, the last one. They're asking a question here. They're asking qualitatively, how will the answer change if a shorter ramp and a steeper angle were used to span the same vertical height? Work done by gravity will not change, but unless work done by friction because of normal force and ramp distance smaller, normal force still does zero work. But less work done by friction. Friction would do less work. If you were to steepen this thing, guys, if you were to steepen this thing, pick it up this way. Pick it up this way. There ain't that much normal force. If there ain't that much normal force, there's not much friction. If you pick this thing straight up, there's no friction at all. This thing's just free falling. There's no frictional work being, there's no friction doing no work to stop what's going on. It's just free fall. The more you elevate this thing, the more you elevate the incline, the more you put an angle, the bigger angle you put on the incline, you will have less normal force. Friction does less work. Stopping you. Friction does less negative work, so to speak. The magnitude of friction's work is smaller. It's a less negative number for the friction work. As far as the fold out is concerned, if you start here and end here, that's all that matters. That won't change. It'll probably get down there faster. It'll slide down there faster as far as the work it does. At that point, you can argue that one too, actually. It would go a little faster because there's no frictional force as well. Let's not open too many cans here, guys. But essentially what they're saying, it's here to here, or if it's something like this, here to here, the work's the same. That's H. That's also H. Assuming obviously I do that horribly, but that's H, that's H. It doesn't matter that one's more of an incline than the other. Okay. That's 5. Okay. Let's go to 9. Looking at 9, you guys. A mechanic pushes a 2.5 times 10 to the 3 kilogram car from rest to the speed of v, doing 5 times 10 to the 3rd joules of work in the process. During this time, the car moves 25 meters, neglecting friction between car and road. Find A. Find out what B is for A. For B, the horizontal force exerted on the car. Okay, not too bad. Okay, so what are they saying here? Again, guys, it's all in the notes as well, so don't, have your book open, look at the book as well, and we'll figure out what they're doing here. The gentleman did some work, and what we're trying to say here is essentially, I'm going to take it off of exponential stuff. A mechanic pushes a 2,500 kilogram car from rest to a speed of v. He is doing 5,000 joules of work. During this time, the car moves 25 meters, neglecting friction between road and car. Find what V is. Find the horizontal force exerted. Okay, this should be pretty straightforward, guys. The work that was done by the gentleman, or by the lady, I mean, whoever is doing this actual work, the work that was done is delta KE. That's the final kinetic energy minus the initial kinetic energy that you built upon. Well, man, I'm going to make life easy for you. The guy pushed it from rest. If it's at rest, there's no kinetic energy. It's all this. The work is going to be, the work he did is 1/2 mv squared. We talked about this, didn't we? Let's solve for B. Why don't you multiply by 2 on each side and divide by m? That's it. It's looking like that. Okay, if it is, let's find out what it is. 2 is 2. We said the person did 5,000 joules of work. That's W. And we said the car was 2,500. Sounds good to me. Grind out the math, guys. It's pretty straightforward stuff. There it is. Period. End of story there. B, what was the force exerted? Work was 1/2 mv squared, but it's also FD. That's how I derived earlier in the lecture. That's how I derived what kinetic energy was. Kinetic energy being 1/2 mv squared. We derived kinetic energy is 1/2 mv squared from this. Let's see what we're doing here. It's pushing straight out. They didn't tell us a whole lot, so we're not going to worry a whole lot. We're going to, F is F equals W. F equals W divided by D. We said 5,000. The guy pushed it. Did he push it 25? Yeah, maybe he pushed it 25. Do the division here. It's the average force he's exerting. The average force he's exerting. Get there. Okay? That was 9. What of 13? It's a neat question in its own right. Problem number 13. A 70-kilogram base runner begins his slide in second base when he's moving at a speed of 4 meters per second. The coefficient of friction between his clothes and earth is 0.70. He slides so that his speed is 0 just as he reaches the base. A. How much mechanical energy is lost due to friction acting on the runner? How far does he slide? It's not a bad thing. We look at something like this. So there's a base runner. He's running. It's baseball. He's trying to get second base. He's going to slide. He's going to figure something out. And basically the way it all goes is he's going really fast. He goes into his slide. And then when he goes into his slide, he's going to keep moving until friction stops him completely. What the heck does that tell you? What it tells me is if the frictional force between the earth and his clothing bring him to a dead stop, all of his kinetic energy went into thermal energy, to say that like the slide, the frictional force creates some sort of thermal energy going on. I'll make a long story short. The amount of work friction did was it robbed all of his kinetic energy, period. So let's see what we got here. All of his kinetic energy is lost to friction, is what I say in my notes. Again, look at the notes, guys. They're going to be pretty good. Hopefully they're pretty decent notes. 13. All of his kinetic energy is lost to friction. So let's figure out what he lost to friction. That's all we're asking. How much was lost to friction? Let's watch out here. All of his kinetic energy. Here it is, 1/2 mv squared. He's moving. All of that will go into friction. All of it will be lost to friction. Mass is 70. 4 meters per second is this. Look, guys, I don't want to nickel and dime you too much, but we know the story here. How much work did friction do on this guy? The amount of work that friction did on this guy is negative. The amount of work that friction did on this guy is negative 560 joules. How much work was lost?
560 joules. How much money did I lose in this business venture? I lost $1,000. I'm not going to say I lost negative $1,000. What's my profit? Yeah, negative 1,000 is my profit. That works. How much did I lose? I know it's a negative already, so I say 1,000. You know this is a negative. The amount of work that friction did is negative 560 joules. But how much is lost? How much money did you lose? I lost $560. You lost 560 joules of kinetic energy. Right. So that's how you write it. That's it. How far do you slide? You know, it's a good question. Well, here's the answer for you. In terms of magnitude, again, I'm not want to nickel and dime this too much, you guys. In terms of magnitude, the normal force is mg. Mu sub k is the coefficient. Normal force is mg. Mg is the normal force times mu sub k. That's the frictional force operating over a distance d. This is going to get us there. What do you mean? Solve for d. What we got? Okay. There's the length of the slide. No, sorry to call it. I'm sorry to say it. Try to think it. 1, 6. Yeah, it's about 4 feet or so, somewhere around there, 3.5, 4 feet, whatever. We'll slide with that. All right, so there it is. That's 13, you guys. Let me see. Is there another thing I? No, that's it. All right. Definitely, this whiteboard has a mind of its own. I mean, it's going to start spinning on its own at this point. I mean, okay. Looking pretty good, guys. Looking all right. Let's go to 17. All right, see what we got. Neat question in its own right. Number 17. A large cruise ship of mass 6.50 times 10 to the 7th kilograms. So it's a very large cruise ship, obviously, guys. A large cruise ship of mass 6.50 times 10 to the 7th kilograms. That's 65 million kilograms. Has a speed of 12 meters per second at some instant. What is the ship's kinetic energy at that time? That's A. B. How much time is required to stop it? That's a neat point in its own right. I'm not thrilled by that question, to be honest with you, but perhaps I'm missing something right here in the immediate sense. What is the magnitude of the constant force required to stop it as it undergoes a displacement of 2.50 kilometers? Okay. There's a lot going on here. There's a ship moving. It's huge. Huge in what sense? It's very massive. It's a massive ship, a lot of mass to it, and it's going at a decent speed. Let's find its kinetic energy. Great. What's the force required to stop it? For some reason, that question, fascinating. Let me go back to what's asking here. How much work is required to stop it? Okay, that's easier. I just read that. I'm sorry. B should be pretty straightforward. If this ship is going very fast and is very massive, it has a lot of kinetic energy. Even if it's not going very fast, it's kind of a relative term anyway. For a ship on the ocean, it's going very fast. Let's see.
if it's going at a particular speed and it's very massive, it's got kinetic energy. How much work is required to stop it? Let me find out its kinetic energy first, you guys. After I find out its kinetic energy, I got more to talk to you about. All of that kinetic energy has to go down to zero. Why is that? Because you don't want it to have kinetic energy. Kinetic energy is energy of motion. I do not want it to have motion energy if this thing's coming to a dead stop. This thing wouldn't come to a dead stop unless its kinetic energy was completely dissipated. The work required to stop it is the work required to take away its kinetic energy. Whatever kinetic energy it has is the work that's required to stop it. Okay, should be pretty straightforward stuff. All right, guys, let's talk a bit. They're talking about this ship, and they want you to know what they're asking you what is kinetic energy. It's pretty straightforward stuff. So let me not delay you too much on this. They want to know the kinetic energy. Kinetic energy is 1/2 mv squared. One half is 1/2. .5 times 10 to the 7th is the mass of the ship. 12 meters per second is the speed. Ladies and gentlemen, there ain't much to do beyond this. I mean, just you grind out the numbers, and you're going to look pretty good. Let me kind of just do this initially, and then let me clean it up a little bit. Let me make it the scientific notation that we're supposed to have. 4.68. That is the amount of kinetic energy. That is the amount of kinetic energy that the ship has. B, how much work is required to stop it? Guys, I got news for you. This is the kinetic energy of the ship. You are going to bring this ship to a dead stop. You're going to rob it of all this. You're going to rob it of all this kinetic energy. You're going to rob this of all its kinetic energy. What does that mean? It basically means how much work. So let me see here exactly how they do it. Because it's kind of a touchy subject how it works here. How much work is required to stop it? I don't know. I'm not thrilled by some of the way this can kind of be said. The magnitude of the work is equal to all of this kinetic energy. The magnitude of the work that you got to do is in the opposite direction to which the ship is moving. You need a magnitude of work forgive me, guys. Come back to A with me, please. Yeah, if I'm going to clean this up, it's got to be here. The 10 to the 7th becomes 10 to the 9th. This is the amount of work that you got to exert on it. Not helping it, going the other way. So the magnitude of the work is equal to all of this KE, 4.68 times 10 to the 9th joules. Therefore, you got to do negative. You got to do some sort of frictional force or some kind of tugboat going the other direction. The tugboat's got to go the other direction from its motion. You got to stop it. It's negative 4.68 times 10 to the 9th joules. So this is the magnitude, and this is really the direction associated with it. So I don't know, it's kind of a touchy subject. I'm kind of careful how I ask stuff like that when I do ask it. But this is technically where the way that they're kind of asking to do it. You say it. Okay? How much force would you have to exert? What is the magnitude of the force that you would have to exert if you're going to stop it at 2.5 kilometers? What is the magnitude of the constant force required? Now, magnitude means a positive number. Magnitude is always greater than or equal to 0, you guys. Magnitude is always greater than or equal to 0. What is the magnitude of the constant force required to stop it as it undergoes a displacement of 2.5 kilometers? What is the magnitude of the constant force? Okay. So for this one, work equals force times distance. You guys, my brakes on my car do not have to be very good if I have a whole block to stop. They better be good enough. They can't be non-existent because I'm not going to stop. But if I need to stop within 2 meters, my brakes better be very good. If I need to stop within 100 meters, they don't need to be as good. What does that mean? The force that the brakes have to exert doesn't have to be that great if I got a whole 1,000 meters to stop the car. If I got a whole 2 meters to stop the car, the force better be great. Because I got to rob the kinetic energy that's present. I got to rob the kinetic energy that's present. You got to take all of this kinetic energy, guys. 1/2 mv squared. You got to take all that kinetic energy. Sorry, I pushed that. I thought I came calm for a second. All right. So 1/2 mv squared. That's all that kinetic energy. I want all of that kinetic energy robbed. I got this right here. I got to find what the force is. That's all I have. It's a great price. It's a neat problem. It's probably a lot easier than I'm making it. A lot of this stuff is easier said than done. I'm trying to discuss this stuff while I'm doing it, you guys, so I think you know where I'm coming from. What's that force equal to? Let's go. Let's keep going. 1/2 mv squared. We already delivered that speech. In terms of magnitude, you got to rob 4.68 times 10 to the 9th joules of kinetic energy from the system. You got to do this in 2.5 kilometers. Everything's got to be the MKS system of units, you guys. You got to go here. When you do this, .872 1.872 times 10 to the 6 newtons. And that's in my notes. That's my notes too. All right, guys, that's 17. Let's go to 25. Kind of a neat one here. Number 25, a daredevil on a motorcycle leaves the end of a ramp with a speed of 35 meters per second, as in the figure. I'll try to draw some. If his speed is 33 meters per second when he reaches the peak of the path, time out. Okay, at the very peak of his, the peak of his flight, because he's in flight at that point, guys. Let me just kind of talk about that a little bit. If his speed is 33.0 meters per second, when he reaches the peak of the path, the peak of his flight, you guys, is what I mean. What is the maximum height that he reaches? Ignore friction and air resistance. Okay, this should be pretty straightforward as well, you guys. Let me get this out of here. We'll start with this one.
What's going on here? Well, look, you know, there's this thing called Occam's razor. You got to make certain assumptions to make this stuff work. So it can get a little messy. I mean, if you don't make the assumption. We're not worried about, I mean, this guy's here, he's on the ramp. Yes, I realize I draw all people like they're bowling balls. I get it, okay? So here's the motorcycle and the person, and I can't draw, obviously, so here we go. And then we go. This guy's flying. Bam, there's a speed here, guys. Gets up high, and he comes back, you know, he'll eventually come back down. There's a ramp that, you know, bring him back down, whatever, we're gonna do that. But anyway. Here is the apex of the Daredevil's flight. Look, they never told us how high the ramp was, did they? They never told us how high the ramp was, so I'll tell you what I'm gonna do. We're gonna take the ramp, and we're gonna assume that it's at height 0. We're gonna make the assumption that right here is height 0. And then from here, we can figure out his height from there. They never told us, hey man, by the way, you know, there's the Earth, and there's the ramp, and actually by the time you took off, that ramp is actually 20 meters high. They never told us that. For our purposes, we'll say that the very top of the ramp is 0 meters high. Now, unless they wrote something here, they didn't. Okay, so we got to play their game. If he's going 35 meters per second, right here, right when he takes off, the initial 35 meters per second. And here, VF, we'll call it VF, I guess, right here. Okay, I'm not trying to sound like, you know, I'm not trying to sound like a complete fool, but we all know that 35 meters per second is a bigger number than 33 meters per second. What does that mean? It tells me that he's going, believe it or not, way up here, he's going slower up here than he's going right there. Yeah, that makes sense, because he made himself into a projectile. It's like he got fired out of a cannon. All this kinetic energy went up here, and some of it became potential energy, and some of it stayed kinetic energy, but it's not as much as it was initially. This stuff's a lot easier done than said. Let's have a look at it. So, this chalk's not that bad, man. I think I got more chalk than I need. The Joe, I'll be okay. I mean, I can always figure this out. And I always feel like telling you guys when I use new chalk. It's like those tennis players. Don't they always show the tennis ball that's going to go fast? I feel like Novak Djokovic. You know, I always say that. I show it. So, all right. So new chalk. Be careful. They go fast. So we're looking at this. What's going on here? We have said energy's conserved, always conserved. This guy is going at a speed VI. That's all kinetic energy. His height, man, 0 is kind of an arbitrary number if you really want to know the truth. We'll say he's at height 0. So we got this. That's the EI. The EF plus MGH. This is the height H right here. There it is, guys. There it is. There it is. You've got plus 0 height
equals 1/2
Let's go.
let me get MGH by itself by subtracting. Let me get MGH by itself by subtracting 1/2 MVF squared inside. Seems counterintuitive almost. Wait, should that VF be in front? Look, we know it's a smaller number. I think we're going to be on the mark here just fine. Let's try a couple things here. There's a lot you could say here actually. Let me go MGH. I got 1/2 M VI squared minus VF squared. I'm going to write it like this. We got this. Let me divide by MG on each side. Divide by MG on each side, guys. You're one there. Okay, fantastic. I think there's enough, man. I'm trying to save what's going on here. We'll definitely get through. There's going to be more than enough here. I think a lot of it has to do with my left-handed idiosyncrasies. More than anything, I can't write a lot. I need the chalk in a particular way, or I start breaking it, I guess. Because I press pretty hard when I use this stuff. So here we go. We're in good shape. So what we're looking at is you divide by MG on each side. When you divide by MG on each side, the M's, divide by M on each side, the M's cancel. Let's just make it easy that way. Divide by G, you got the 2G on the bottom, and there's the ticket, guys. This is what's going to get you there, and that's it. It's about as simple as that. When you plug in the numbers, it should work okay. I mean, you got H, you've got 35, the initial, 33, the final, 2 times 9.8 on the bottom here. Should be pretty straightforward, guys. Should be pretty straightforward. You knock it out. How high this guy get? I think it was this. You just check it. I just saw it on a glance. Make sure it's right. Yeah. It's 6.94 meters to the height. Conservation of energy. The bread and butter is right here. Bread and butter is right here. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Grind it out, it's going to work. It's going to work great. That's how high you got. Not pretty high. About 20 feet, 21 feet or so. Got up there. 21, between 20 and 22 feet, something like that, I guess. All right. That's 25, you guys. So, let's go to 38. All right, guys. For 38, let's see where this is going. For 38, they talk about a situation. There are 2 blocks. 2 blocks are connected by a light string that passes over a frictionless pulley. The system is released from rest. 0 velocity initial is what it means. While M2 is on the floor and M1 is a distance h above the floor, assume M1 is heavier than M2. Or assume M1 is more massive than M2. Find an expression for the speed of M1 just as it reached the floor. B, taking M1 to be 6.5 kilograms, M2 to be 4.2 kilograms, and H to be 3.2 meters. Evaluate your answer to part A. And C, find the speed of each block when M1 is fallen a distance 1.6. Okay. This isn't quite as scary as you think it is to get the problem done. But you know, we'll work on it. We'll figure out where we're going here. Let me draw this. Let's use what they have. They're talking about a pulley that is massless and frictionless. So there's no mass associated with it, no friction associated with it. So it's going to be a pulley. There's two things. The masses are both connected to it. One mass is on the ground, not moving. The other mass is up in the air. It's heavier than the other one. So, and when you let it go, it's going to go down and pick the other one up. And so there's going to be a change in what's happening here. I don't know how fast it's going right at the bottom. And see what we can say here. All right. So with this in mind, you guys, okay, well, all right. It's easier done than said. Let me try to think exactly what I want to say here. Yeah, I think it's more. The problem sounds more intimidating than it actually is. Let's see what we can say about it. So they got two blocks, and they want you just to explore what the heck's happening here. Okay. That's pretty legible, right? The masses and stuff there. Okay. So we're looking. I mean, I'm trying to make. I sort of exaggerated it, but maybe that's okay. I don't know. We'll see. I got M1. M1 is more massive than M2, so I kind of drew it that way, so to speak. There's a height right here. All right, there's a height H, and then they're asking, okay, assuming this, find an expression for the speed of M1 just as it reaches the floor. Then they actually plug in some actual numbers in there. They want you to evaluate your answer as part A that way. And then B, find the speed of each block when M1 is falling at a distance of 1.6. All right. Again, it's harder to explain than it is to do, you guys. So let me just try to make a little bit of sense. Look, there's a number of ways you could play the game on this thing. I don't know if there's very many number of ways you can do it, but I think there's definitely more than one way, actually. I know for sure there's more than one way to do this. I think the easiest way to do it is by energy considerations, and of course the chapter that we're on pertains to energy considerations, so we should be okay. All right, let's talk. We've got, this thing is massless, the axle is frictionless, it moves, it's not an issue. These guys are kind of calling the shots on the whole thing. Nobody is moving in the beginning. What does that mean? Nobody moving in the beginning means the only energy that's present here in the mechanical sense is potential energy. Mechanical potential energy is the only thing present. What does that mean? I'll make a long story short, nobody's moving. This guy's attached to this thing. he ain't gonna fall. He's massless anyway, but let's say there was a mass to it. This thing's connected in such a way it's never gonna fall, it's never gonna stretch. The rotation is not gonna be an issue for us, so I have to say it's massless. Okay. I'll make a long story short, you guys. All the potential energy is this guy. This guy ain't moving and he's got no height. All of his potential energy. Here. At the end, this guy will climb. By the way, how high will he climb? If this guy falls a distance h, and the rope doesn't snap, the rope doesn't stretch, nothing else happens, the pulley doesn't get lowered, the answer to the question is quite easy. If this guy falls h, this guy rises h. Let's see what we got here. Make a long story short. Well, here it is. M1GH is the potential energy of the system initially. There ain't no kinetic energy because the system's at rest. The system's at rest. There is no potential energy. Forgive me. There is no kinetic energy. It's all potential energy. At the bottom, when this guy falls, he will be in possession of kinetic energy. At the top, M2 will also be in possession of kinetic energy. They're both moving. You guys, they're both moving. At the bottom, if the guy, right before he hits the ground, right before this guy hits the ground, he's going at a speed v. They're attached to the same rope. This guy's also going at a speed v. 1/2 m1v squared plus 1/2 m2v squared is what's going on. That's interesting. We'll talk about that in a second. In addition to that, at the very top, this guy now has potential energy that he never had. Down here, he never had. He lost all his potential energy. All his potential energy that was lost went into his kinetic energy, into the other guy's kinetic energy, and into the potential energy of the other guy. Pretty significant. So what do we got going on here? I guess that makes sense. It makes a lot of sense. Look what I'm doing. So it makes a lot of sense. Why does it make a lot of sense? It makes a lot of sense because they're connected. Guys, this guy is falling. This guy is falling down at the same rate that this guy's climbing up. It's as though they're attached. It's as though it is the fact that they're attached. They're attached by a rope. They're both moving at the same, yeah, they may be separated in this elevator system. It really is that they're connected. There is no, it's like, it really is. Subtract over here. Subtract M2GH over here. I'm not done. I'm not done. But that's true. I'm not done. But, look at it. Look at it. It looks kind of neat. The rest is math. What do you say you multiply, get rid of that 2. What do you say you multiply by 2 on each side, divide by the quantity, m1 plus m2, and then you got v squared. Now we said m1 was bigger than m2, so we're okay here. I'm not running into any kind of trouble yet. Sounds good to me. Square root both sides.
Good, thank you.
Okay, so we're looking pretty good. Yeah, that's the way it's looking, guys. This answers A, it's kind of going to be the key for everything else we're doing, or a lot of the stuff we're doing, to be honest with you. Maybe the key to all of what we're going to be doing in that regard. This is big. This is big. This answers a lot. This answers a whole lot, you guys. This answers a whole lot. So, now they're asking us, why don't you, yeah, for B and C, it's going to be cakewalk, guys. For B, they're asking you, they're telling you this. I'll kind of, you'll fill in the blank. You got this in my notes in Canvas as well. You got this in Canvas as well, look at the numbers. You've got the book. We open the book, we look at it, we're all good on this whole topic, you guys. 2 is 2. They're saying if M1 is 6.5 kilograms, and M2 is 4.2 kilograms, and this is 9.8 meters per second, and the height from which it's released is 3.2 meters, and we said this was 6.5 and this was 4.2. Basically what they're doing is, what if, ladies and gentlemen, they told us that M1 was 6.5 kilograms, M2 was 4.2 kilograms, G was 9.8 meters per second. This H is 3.2 meters. This is 6.5 kilograms. This is 4.2 kilograms. And there it is. And there it is. You plug it in there. So if I put 6.5 right here and 4.2 right here, 6.5 right here and 4.2 right here, the 9.8 and the 3.2, man, just grind it out. You grind it out, what's the speed going to be? What's the speed going to be now? Let's talk about that. I mean, this is going to be 2.6 meters per second. What does that mean? That means right before this guy hits the bottom, M1 hits the bottom, he's going 2.6 meters per second. Right before this guy reaches the apex of his journey, he's going also 2.6 meters per second. So that's A and B, guys. Not too bad. Forgive me, okay. Okay, guys, this should have been the answer to C. B is something different. Forgive me, guys. I'm sorry about that. Let me go here. I'm going to erase a little bit more. I don't think this is going to be a problem. The big thing, and I don't want to beat this thing to the ground completely, guys. This right here, I cannot overemphasize, I don't think. I cannot overemphasize the importance of the mathematics here. Once we've gotten to here, that's going to be everything on this, guys, for A. So if you go to B, forgive me on that, guys, I'm going to have to redo it. It's the same mathematics. So again, they're saying if M1 is 6.5 kilograms and M2 is 4.2 kilograms, and that's 9.8, and this is 3.2 meters, and that's 6.5 kilograms again, and 4.2 kilograms again. Put those numbers in here, grind it out. B is equal to, I don't know how I missed that, guys, it was right in front of me and I missed it, forgive me. That's 3.67 meters per second. For C, they're saying, what is the speed when the when the object, and let's see which one they said here, this is kind of an interesting point in its own right. When M1 has fallen 1.6 meters, when it's fallen 1.6 meters, how high is it? Now they're doing some stuff to us here. I'm gonna try to figure something out here, a little bit of what they're saying here. Yeah, when it fell that high, when it fell that much, the other one climbed that much. So, lost, gained, okay, that'll still work. Okay, that'll work. One of them's going to climb. If this guy falls 1.6 meters, this guy will climb 1.6 meters. If he climbs 1.6 meters, the way we wanted to say it is, yeah, right. The loss of one, the gain of the other, we are going to say that the difference here will go into, it's a little bit of a complicated story. I'd rather have everybody in front of me when I'm talking about this one, to be honest with you. But basically, the argument here would be the change in the potential energy. This guy loses more potential energy than this guy gains. And the difference between the two will be manifested in the change in kinetic energy. So let's take the fall of 1.6 to be equivalent. At the fall of 1.6, the other guy rises 1.6. That'll work. The fall of 1.6 will tell you this guy will lose more potential energy than this guy gains potential energy. The difference in the two potential energies goes into the kinetic energy. This is perfect, guys. This works just great. Plug in everything. Instead of putting 3.2 right here, put 1.6 right here. Say that again. Instead of putting 3.2 right here, because that was the first instance. It was a fall of 3.2 and a rise of 3.2. The small guy rose 3.2, the big guy fell 3.2. Here, the big guy's going to fall, not 3.2, but 1.6. And the small guy's going to rise 1.6. Put a 1.6 here. If that is the case, it's half as much. It's half as big. So what you have here is everything else is the same. 6.5 right here, 4.2 right here, 6.5 right here, 4.2 right here. The 2, the 9.8, 1.6 right here. Grind it out. Here's where, and again, the 6.5 and the 4.2 as we said. This is going to be and that's this guy. And that's what I made the mistake, I put it in for B. But that's C. That's when there's a fall of 1.6 meters. Here's when there's a fall of 3.2 meters. And there you go. There you go. All right. Looking pretty good, guys. Looking pretty good. We're doing this. Let me go to 43. So we're looking okay, guys. We're doing okay. And of course, I now have chalk all over me. I always want to get the catch. Okay, guys. Doing pretty good. Doing all right. So let's go. Let's try to knock this out. Let's try to go in an efficient manner here. Let's see what we can do. So 38's out of there. We got 43 and 85.
43, it's a neat question. Let's be careful with it. It's a great question. For number 43, excuse me, just 1 second. Okay. 43, the system shown that I'm about to draw you guys is used to lift an object of mass 76 kilograms. A constant downward force of magnitude F is applied to the loose end of the rope, such that the hanging object moves upward at a constant speed. Neglecting the masses of the rope and the pulleys. Find the required value of F. That's A. B, the tensions T1, T2, and T3. C, the work done by the applied force in raising the object a distance of 1.8 meters. Okay. This is a rather interesting problem. Let me try to be careful with how I do it. All right, guys, it's looking. Okay, here's a pulley. There's another pulley. This pulley can move upward. Mass M. There's a lot to say here, guys. I won't do this. A lot here. I remember the drawing was not drawn, in my opinion, the way they kind of depicted the whole thing. This is a rope right here, guys. This is a rope. It ain't gonna move, but there's a rope right there. There's a tension T3 associated with it. There is a tension T2 rather, I'm sorry, associated with this. This is T1. Figure out exactly what I want to say here. You're going to pull this thing down that way with force F. And we got to talk. Just trying to see exactly what I want to say here. There's the tensions. There is a tension right, the mass right here. Let me put it like this in the notes. Everybody understands that's mg going straight down. We're going up at a constant speed, no acceleration. So this guy is, well, let's see what this guy is actually. This is mg. And, you know, it's gonna be a little, I almost regret writing that mg down there, you guys, but I'll say, okay, there's a tension going straight down. There's also a tension going up. Remember, we got Newton's third law, so we can draw this a whole bunch of ways. But there's a tension going straight down called T2. I got something to ask you. If this thing is moving, you know, this guy's yanking this way, but he's yanking this way, but he's being held up by this guy. He's also being held up by that guy. We'll call. Oh, thank you.
Come from Mike Ford. Oh, you're welcome.
Appreciate it. Thank you. So, look, there's a number of ways to say this, and I guess I should just say it. If this guy is pulling down, we'll call the pull down associated with the fact that there's a mass there. It's mg.
We'll call this pull down, the T2. It's pulling down with a force of F prime. Call it F prime. This guy is F prime over 2. And this guy is F prime over 2. F prime, so F prime over 2. It's the way it is. So, and then this is the F right here. If this is F prime over 2, now there's just so much on here. I'm trying to not overwhelm the whole matter here. I think there's almost no way around it. Again, my notes should look better than this does. But this shouldn't look too bad, I hope. That's this guy. That's this guy. Just go over here. Go over here. F prime over 2, F prime over 2. This is F prime straight down. Sounds good to me. There is, from action reaction, there's an F prime over 2 right here. And the pull you do, the pull you're going to do to get the F prime here is also an F, that's also going to be F prime over 2. So that's this guy. What's going on here? There's an F prime over 2 pulling this way, and an F prime over 2 pulling that way. F prime over 2 and F prime over 2. F prime over 2 and F prime over 2, both pulling down. F prime over 2 plus F prime over 2. That guy right there is going to be F prime. You're adding that. This guy is F prime over 2 as well. This is T2, which is equal to F prime. And this is T1, which is F prime over 2. All right, let's see what we got here. It's a little, to say it's a mess is almost in the realm of the understatement there, I guess you would say. But what do we got here? We basically got the T3, which is this right here, is the sum of these two guys, which is F prime. The T1, we said was F prime over 2. The T2 down here is totally F prime. So I'm sorry, forgive me. The T3 was that. The T2 was F prime also. Sounds good. Let's see here. And let's see here, guys. Let's see what I did here. Yeah, T2 and T3 is that, and then that T1 is that, right? That should be fine. So what do we got here, guys? What we have here now we get enough chalk for the next 5 semesters, I think, right? So we're all right, let's see that, guys. We're talking about T1 is F prime over 2. T2 is F prime
And what's what, man? I mean, well, right here, we just said all that straight down is mg. You know, F prime is mg. And let's see here, the mass is 76 kilograms. So 76 kilograms times 9.8. And there we go. I think we got all that, guys. What we have here, F prime and again, my notes are a little more organized in this particular presentation right here, guys. It should be okay. I mean, T1 is this. T2 is this. T3 they should all be there for you. Let's see what they got here. Let's see exactly those. Should be on the mark. Yeah, should be okay. We got the T1, the 372.4. The T1 is 372.4 newtons, and the T2 and the T3 got them equal like that, and I think we're good. I think we're all right. Fascinating issue. The moving pulley gives an advantage at the cost of extra distance required. So there's an advantage here. You don't get something for nothing. You don't have to have as much force in these parts of the cable to get the lift to happen. Half as much force is needed is the actual force associated with the lift. 1,000 newtons of a lift, 500 newtons here and 500 newtons here will give you the 1,000 when they're helping each other out. The moving pulley gives an advantage. The moving pulley gives an advantage at the cost of extra distance required. To move the weight 1.8 meters required 3.6 meters of rope consumed or moved in the process. In other words, yeah, you might be able to move this thing. Look, guys, see that right here? See the mass? I might be able to move this thing from here up to here, 1.8 meters. But I'm going to have to move the rope double that distance to make the lift of 1.8 meters. You know, the moving pulley gives an advantage at the cost of extra distance required. To move the weight 1.8 meters required 3.6 meters of rope consumed or moved in the process. So what they're saying here is, I think so we've got the answers here for those two. Find the required value of F to do this. F is equal to F prime. I think I should not have called it F prime. F and F prime are the same. F is not. F is this. The force is half. The force I need here, F, is half of the weight. The weight is 744.8. Half of that is 372.4. F is 372.4. That's the force. Wow, it's magic. I need half. People think that it's magic. What's going on here? This is half the force required. Man, if I were lifting this, me standing right under it and trying to lift it, I would have to give it that's what I need to do. Wow, you mean I can lift it with half as much force? How can I do that? What's the trick?
Well, yeah, you are lifting something that's 744.8 newtons. It's 744.8 newtons what you're lifting. And you're only using half that force to lift it? Yeah, but you gotta move the rope twice as far. That's the difference. That's the difference. This guy right here, you know, you could take this guy and say 372.4. Yeah, but you gotta exert that force over 3.6. That's the same as 744.8 going at just half the, yeah, they're the same product though. You don't get something for nothing. The work is the same. The work is the same. So you be my guest. Multiply this and this, or multiply that, you know, multiply this and this, or multiply that and that, and you still get the same thing. Doesn't matter, you get the same thing. Well, what is it? Let's get to it. You don't get something for nothing. You did get a chance to use less force. Maybe I'm not strong enough, and I have to use less force. Great. You better be willing to spend a lot of time pulling it. You better be willing to spend a lot of distance of rope pulling it. You don't get something for nothing. And that's going to be, and this is the work that's done to do that. Okay? The work done by the applied force in raising the object a distance of 1.8 meters, be my guest. It's 744.8 times 1.8. That's the work. Or it's 3.6 because you're pulling twice as far. It's 3.6 times half of what this is. Same answer. Very important. Very important. All right, guys, let's knock this out. Maybe do it in about 10 minutes. That's the goal, right? I always say that, and 3 hours later I'm talking, right? That's just the way it is. But we can do it. I think we're good. So we got this. Let's look at the last one here. The last one here, you guys, is 85 in the book. 3 objects with masses, M1, M2, and M3, 5 kilograms, 10 kilograms, and 15 kilograms, respectively, are attached by strings over frictionless pulleys as indicated. The horizontal surface exerts a force of friction of 30 newtons on M2. Okay, there is a force of friction there. If the system is released from rest, use energy concepts to find the speed of M3 after it moves down 4 meters. This should go pretty smooth, guys. So let's see what we got. All right, guys, this energy concept stuff should be pretty good. It should be pretty smooth in the process. I'll give you the drawing of it. We'll solve it symbolically. We'll plug in the numbers that we need. I think we're going to be okay. They made it, I think, easier than they otherwise could have made it. So that's okay, too. I mean, all right, guys. Essentially, from left to right, we're going to drop the biggest, let's see, 5, 10, 15, left to right, let's see, 30. Okay, should be pretty smooth, guys. Okay. Here we go again, these tables are something else. I mean, massless, frictionless pulleys. This is M2. Drawn some kind of scale here, guys. That's M2. That's M3. They are telling us that this guy's experiencing a force of friction equal to 30 newtons. They are also telling us M1 is 5 kilograms. M2 is 10 kilograms. Okay. They're telling us a lot. They're telling us they started the whole thing from rest. It's released from rest. So here's what's going on, guys. There's a lot of what ifs, but we're not going to worry about too many what ifs. We know, based on what they told us, that if I'm able to hold this weight up, if I'm able to hold this weight up and I'm able to hold that weight up, nobody's moving, and the friction doesn't come into account until motion starts. So we're holding both these up, or we got them attached to some machine that's holding both up. We hit the switch, the automatic arms that are on the machine go away, and this system does this. The thing falls. It falls this way, it moves this way, it moves this way. At any given point, everybody's going at the same speed because they're all attached. So they're asking here, given this right here, the Jordan system exists. If the system is released from rest, use energy concepts to find the speed of M3 after it moves down 4 meters. It's going to fall 4 meters. So I'm going to say this guy's going to drop. It's going to drop a distance h. Okay? So you got this. All right, so I think we're doing pretty good. How do you want to say this? Well, I'll tell you what I'm going to do. As far as I'm concerned, there's a lot going on here. When the automatic machine is holding this thing in place, nobody's moving. When the automatic arms are moved after you hit the switch, this thing starts moving. What do you say? We called the system initially not moving. Let's look at its potential energy initially. There's no kinetic energy initially. There's no kinetic energy initially. There's all potential energy. Then, after this thing is moved, you understand something, ladies and gentlemen. If this thing right here, M3, falls H, it loses potential energy. This guy ends up rising H. This guy doesn't lose potential energy, but he loses the work of moving this guy, F times H, is the work that friction did in terms of magnitude. Let's get down to business, guys. I think the whole matter is this. Initially, nobody's moving. Initially, everybody has potential energy. So I'm thinking figure out what we're doing here. Okay. Let's call this guy, there's a lot of ways to write this. Let me write this carefully. All right, here's what I'm going to say. We're going to make this, I think, pretty easy to handle. We do it. Let me think what I want to say. We've got, it's like I'm looking for answers and I don't have my students here, man. This is where I ask the rhetorical questions. What do you guys think? You know, get myself off the hook here. I'm not afraid about how I'm going to do this. I'm thinking of, I'm looking at my notes and I don't think there's anything wrong with the notes. I'm just trying to figure out, okay, tell what I'm going to do. You tell me how you feel. Everybody's going to tell me, when we all meet together, hopefully soon, right? You guys can tell me how you feel about this. You can look at my notes as well. We're going to take this guy. Nobody's moving. There's those automatic arms holding these in place. This guy's being held down. This guy's being held up. He's not allowed to go up. He's not allowed to go down. Let's leave it alone. This guy is going to be the driver of everything, in a sense. I'll tell you what. He's going to fall the total distance of H. M3GH. M3GH means he's going to lose M3GH of potential energy. Period. True. I don't know exactly what I want to say here. All of that is going to do the following. When he loses a height of H, when M3 loses a height of H, M3GH, bam, he lost that. What happened when he lost that? What happened when he lost that is he gave M1GH potential energy. He also did work, FH, against friction. In addition to that, when he does that, he is going to be moving at a certain speed. So he gained kinetic energy. By the way, so did the guy that was being affected by friction, and so did M1. Pretty fascinating stuff. Let's do it like this then. Let me get all these guys onto one side. Let's get these guys together. 1/2 M1 plus M2 plus M3. Look carefully, guys. Look carefully, guys. Look carefully. Wow. It's as though they're connected. It's as though they're all riding on the same wagon. Yeah, they are. It's called the rope. The rope's moving all of them. The rope's moving all of them. They got all this kinetic energy, and all that kinetic energy that they gained, how did that happen? Let me subtract this guy. Let me subtract this guy inside. Let's subtract that guy inside. We got M3 GH minus M1 GH minus FH. We'll talk. We're going to talk. Let's try again. Got this. I'm good. The difference in these two potential energies, minus the work that you had to do to beat up friction, M3 M3G minus M1G minus F. I don't think I wrote it like that, but it kind of, right now it's aesthetically like not a bad way to write it. What's going on here? There is a pulling contest. Basically, this is probably a better one than even what I did right here. It's the same thing. Whatever potential energy was lost had to go into giving the other guy extra potential energy and into beating up friction. Whatever's left over is going to give you the change in kinetic energy. That's important enough that it needs to be said again. My brother-in-law always gives me a hard time. I always repeat myself. The guy in Goodfellas, Jimmy Two-Time, right? Remember I say that? I don't see it twice. I don't feel it. So, okay, this has got to be said. This is very important, guys. Maybe the argument here makes more sense. I was a little apprehensive at first. You saw me thinking about this. Okay, you saw me thinking about this. This is not the only way to do it. We can do it a bunch of other ways. We all mean the same thing. But I got to talk to you. What I got to tell you is this. The guy who's got the most to lose is the most massive of the objects. And therefore, it's going to go down. M3 is going to go down. M3GH is going to fall down. Its fall down is a loss of potential energy. It ain't ever lost. That loss of potential energy went into the system somewhere else. This guy lost that much potential energy. You know where it went? I'll tell you where it went. All that potential energy lost, some of it went to giving the other guy more potential energy to climb. He climbed. The difference between the potential energy that he gave up, some of it went here, some of it went to fight friction. So take that and take that away from that. What's left over had to go to kinetic energy. That's huge. That's huge. That's huge. That's big. The rest is math. The rest is nothing. The rest is not bad. They got different ways they can write this, and that's it. So you got it written down here. You've got the reverse feature. So you got it here. Let me erase it. Let me say, what would I do here? How would I multiply by 2 on each side and then divide by this quantity? Notice, that thing's all attached. Yeah, there's the same rope holding all of them. There's the same rope holding all of them. Of course they're attached. Multiply by 2 on each side and divide by this, and I think you're good. And then you got B squared. I think it should be okay. All right. So, okay, got it, guys, and we'll be able to go back. Okay. We're looking good. I mean, everything's fine, guys. You play the game here. Do the manipulation. Do the stuff I just told you to do. Do the stuff I asked you to do just now. And I think you're looking okay. The rest is, it's kind of artistic license at that point. Exactly how you want to write the thing. Some neat mathematics, guys. I want to say one thing right when we finish this thing. And I think you already kind of gathered from the stuff we're talking about. Get it to here. The rest is a cakewalk, guys. The rest is not bad. The rest is not bad. We got 2H. We got M3G. It's the way this stuff gets moved around, I think it's more confusing when you move around it. It's easier to look at it aesthetically, but you don't always get the sense of what was going on the way we left it earlier. But you're here, you got this, M1, M2, M3. It's looking good to me. I mean, it's right there. That's good. Now the rest is what you know. They told you. I think they said 4 meters on that one. I'll just quickly see. It fell 4 meters. If the system rate use energy concepts to find the speed of M3 after it moves down 4 meters. Okay. So H is 4 meters. M1, M2, M3 is 5, 10, and 15 respectively. Guys, 5, 10, and 15 respectively. 15 here, 5 here, 30 here, 4 here. The rest is math. How fast is it going after it fell 4 meters? .26 meters per second. 4.26 meters per second. Neat stuff. If this guy was a bigger number, he would hamper the motion. Friction's of course going to hamper the motion. If M3 is a lot bigger, if this M3 was not 15 and this M1 was not 5, if this guy was not 15, let's say it was 50, and then let's say that was 5. That's a lot more difference, and that's going to help the number be bigger. If the fall down is bigger, that's going to help the number be bigger. There's a lot here, guys. This is it. This is what I wanted to say. The one last thing I want, I'm still on real quick. The one last thing, this is all I wanted to say, guys. The big thing is this. It's not about plugging in answers. I've had my differences with students in the past where they made, claims have been made regarding, I did it this way, I did what you showed me. You've got to go beyond just being able to look. I mean, looking something up is great, but what I had an old professor used to tell us, an old professor, really good man, really decent person, he said, it was an engineering class, and they will not hire you for you to go and look something up. Some of what you're going to do is look something up, I get it, but they won't hire you for just looking something up. You have to be able to think on your own. This right here, you can't just, you can't always go with, okay, there's a cookie cutter approach to this, there's a recipe to this, there's a map to this. There certainly is. But you have to think your way through it. And like that great professor had said, they would never hire, they don't hire engineers just to be able to look something up. They hire them to, not only be able to look things up, but also to kind of like think outside of the box and really be intuitive and really in an innovative way and look at what it is that you need to know. It's a very, very important concept. We'll talk in person, hopefully soon, guys. That's it. Thank you very much.